Okay, mm, mm, mm. Okay, last time have we started the introduction to the statistical learning, and we talk about what is statistical learning, what is the bias variance trade-off, which is the fundamental principle behind machine learning and the statistical learnings. So I think we stop here. So these are I will show you two simulations. And these two simulations will help you to better understand uh, what is an optimal model. Okay, so there's a common misunderstanding that the optimal model is the truth, and that is not right. Okay, so optimal model, as I said last time, depends on the purpose of the study. What do we mean by optimal? For the predictions or for the interpretations or what, right? And also based on, also this is optimal model depends on the complexity of the underlying mechanisms and also the quality of the data and the sample size. So I will cover that through these two simulations. So why we need to do the simulations? Because in the simulations, we know what is the truth because we designed that experiment. Okay. For example, in this study, we have uh, 500 samples with 25x and one response y. And the data generating mechanism is what we designed is yi equals to what? To the summation of the first 15 x variables plus some additive noise. And this additive noise is following a normal distribution with mean equals to 0 and variance is 9, right? So we know the truth. Okay, so here the x, we have 25x, right? It follows a MVN, that means it's a multivariate normal distribution. Okay, with the mean is 0, that means all the x have the mean equal to 0, and the variance covariance matrix follows this. So anyway, this is the design of that simulation. So we know the truth. Okay, so then you can see, although we have 25 variables, only the first 15 variables are relevant to the y. The rest of the 10 variables are irrelevant to the y. Okay, so let's use the best subset selection to find out the optimal models. The best subset selection is in the library LEAPS that I mentioned last time. So we also have two groups of model generated. First is using the 50 observations, the first 50. And the second is to use the full data set, which contains 500. Okay, so let's see. This is the code, sample code, and this for the best subset, these are the parameters that I used, MV max and M best. Okay, so you can see here, the top row is for the small sample size situation. I only have 50 observations for the top row, but for the bottom row, that's for the full data set, which we have 500. Okay, so I do variable, I select the models. Remember, using the best subset, we can select model based on what criteria. We can choose like R squares, but here I'm using Mallow CP and BIC. What is BIC? BIC is Bayesian information criteria. Mallow CP, these are the two common criteria. So basically, the information is the model that gives us the small values for the Mallow CP or the smallest value for the BIC, these are the best model. So here the simple message is I use this criteria to select what is the best model. The smaller the better. Okay, and why? What is the horizontal axis? Horizontal axis is the model size. So that means how many variables do we contain in the model? And why we have multiple points on the same for the same model size, that is obvious because like when the model size is 1, right? That means we contain all the univariate models. How many univariate models can we have? We can have a lot. We can have 25. Remember, we have 25 x variables, right? So that's why I'm just listing the top 5 with the smallest BIC. Why? Because look, what is the M best? M best, I'm only selecting the number of subset that has the best performance at each model size. Okay, so I believe you see, I set the M best to be 5. M best to be 5. Okay, so that's why I only show the top 5 best models for each model size. Okay, so for when the sample size is 50, you can see what is the optimal model. The optimal model size is around 10 variables. And for the Bayesian information criteria, it's around 8 to 10. These seems to be the best, right? But what is the true model size? The true model size is what? Remember, it's 15. Why? The response variable is only relevant to the first 15 x variable because that's a simulation, right? But when we have the sample size is 500, you can see using the MALO-CP and the BIC, we got 15. They are both the optimal model size. So now you can see from this simple simulation, you can see what? The sample size effect. So that's what I mean here. The optimal model depends on what? Depends on the sample size also. So the optimal model that you got may not be the true model because it depends on how much sample size that you have. What does that mean? That means if we have a large sample size, that means we have more information available to identify the true model. Of course, if we have sufficient amount of information for us to identify the true model, we definitely can find the true model, which only includes the first 15 variables. But if the sample size is not large enough, like 50, that means we don't have sufficient amount of information to help us to find out the true model. But what we can have is find the model that is closest to the true model based on how much information that we have. Okay, so that's the sample size effect. And also in this simulation, I also examine the noise effect. So I set 2 levels of standard deviations on the additive noise, 1 and 6. Okay, so when the standard deviation for the epsilon I, so here when I do this, I can set the standard deviation for the additive noise. Epsilon I follows the normal with mean is 0, mean always 0. I don't change that, but I can change the variance or the standard deviation, right? So here I'm replacing the 3 as the standard deviation. In here, I'm changing it to 1 and 6. Okay, so now in this study, to examine the noise effect, we have 2 scenarios. One for the SD is 1, one for the SD is 6. So how do we quantify the data quality? Usually we use the SNR, signal noise ratio, to identify the data quality. So what is SNR? Signal noise ratio is the ratio for the variance for the true signal, true function f over the variance for the random errors. Like here, when the standard deviation is 1, the variance for the noise is 1. But for 6, the variance for the noise is 36. Okay, so when the epsilon equals to 1 and 6, that corresponds to SNR equals to 122 and 3.4. So the larger the SNR, the higher the data quality. And that's obvious, right? Because the noise has low variance compared to the signal. That means we have a good quality of the data because the noise has only small variance compared to the signals. So we can easily identify the signals. So these are the SNRs for this study. Okay, so when the standard deviation is 1, that means we have a very high quality of the data. And with the SNR is 122. Okay, so that means the signal magnitude is over 100 times larger than the magnitude of the noise variance level. So that's good. So in that case, in the high data quality case, you can see we can easily find out the true model size, which is 15, because we have a very good data set, good quality of the data set. So we can find the truth, which is 15, right? But when the signal noise ratio is low, we have a high noise in the data set. So you can see the optimal one is 12, which is not 15. Okay, so this also tells you the noise effect. What is the optimal model? It depends on the quality of the data. If we have a high quality, the optimal model may be exactly the same as true model. But when the data quality is low, it's away from the true model. So it really depends. Optimal model is not the true model. Okay, it depends on many factors. Okay, the second simulation is to help you to understand the bias variance trade-off. Okay, so here, just like the first one, I designed the data generating mechanism. So y is generated from a nonlinear function. So this part that I circle, that is fx. Okay, so that's fxi plus the random noise, that's the epsilon I, right? And that equals to yi. Is that right? So that is exactly the assumption that we have. Okay, so this is a very flexible model assumption. So in this plot, you can see the red curve. That is the true function. Okay, and for the training set, we have 20 observations. Okay, and we have a test set. But in this test set, we don't have any noise. We just have the true value. We only have the value for the f. Okay, so this is kind of special. Okay, this is different from the real data. Real data, we don't have the true value. We have the corrupted value with additive noise. Okay, but this is just for the demonstration purpose. Okay, so let's see. And these open circles are the realizations on these true functions. Okay, with additive noise. So how to fit this? I use polynomial regressions. So polynomial regressions is like the special case for the polynomial regression contains the multiple linear contains the linear regression, right? With the order is 1, that's linear regression. When the order is 2 for the polynomial, that's the quadratic model. When the order is 3, that's cubic model, and so on. Okay, so here I'm trying to find out what is the optimal polynomial models to fit the underlying true function. Okay, so I'm examining 10 possible choice. From the order is 1, that's the linear model, to the order is 10. That's the polynomial regression model with the highest order equals to 10. Okay, so you can see we have several curves. So the solid black curve, that's the solid red curve, that's the true function. Okay, so these blue curves, these are the fitted polynomial models from order is 1. When the order is 1, you can see the light blue one, light blue line, that's the fitted linear model, and so on. We have 10 models. So which one is the best? Right? So let's see. First, I repeated 50 times on randomly generated Y's. So for the training set, I randomly generated 50 training set. Because that's a simulation. We know the truth. We can generate these data as many as we want, right? So I generated 50 data set. So each training set, I fitted a model. Okay. So here, let's see. I showed you 3 orders. When the order is 1, you can see in the background, we see the dark lines. These are each line is a fitted linear model for each data set. Okay. And the red curve is the true function. Now you can easily see the bias. What is the bias? Let's say, suppose we want to estimate when the x is 3. Okay, so when the x is 3, what is the true value? The true value is this one, right? Is around 1, y equals to 1. Is that right? But for when the order is 1, when we have a linear model, you can see the bias is very high. Because when we use the linear model, the bias is the distance between the y equals to 1 when x is 3 up to, for the linear model, that is closest to 2.5. So the bias is about 1.5, something like that. Or maybe 2, yeah. Right? So you can see that depends on, oh, yeah, that's about equals to 3. So 1 and 3, that's the difference is 2. Okay, so the bottom one shows the bias and the variance. So you can see this is the true value. So this one, this tick mark at the bottom, that's the true value. That's the value for the red curve when x is 3. So that is around 1. Is that right? But the distribution on the right side, that's what? These are the 50 values based on the random model. You see that? We have 50 models, right? When the x is 3, we have those 50 predicted values. And for these 50 values, I draw a histogram or a density plot. And that is the density plot for all these 50 values. And what is that red dash line at the bottom? That's the average, or that's the center of the density distribution, of the density curve. So you can see the center is around 3. But the true value, which is this one, okay, that equals to 1, right? So that's 1. So what is the bias? Bias is the difference between these two. So the bias equals to what? 2. You see that? I showed it on the top. And what is the standard deviation? That means what is the standard deviation for this model? It's 0.284. Okay, so that's the linear model. But now I increase to the 5th order. When the order is 5, you can see the bias decreases to 1.3. Remember, this one is 2. This one is 1.3. But the standard deviation increases to 0.3. But this one is 0.28. Okay, but this is the order of 10. When we have the 10th order, among these 50 models, you can see the bias is almost 0. You see that? The bias is almost 0. But the standard deviation is very high, is 1 point something. That's the biggest. You see that? So that is the purpose for this simulation. I want you to, through this simulation, you understand what is the bias, what is the variance, and why we need to talk about the bias variance trade-off. Okay? So what is that? So the main point is I want where is that plot? Let me see. I want you to, so the main point through that simulation is I want you to still remember that this fundamental picture. Okay, so when we have a high model flexibility, the model is complicated, like the polynomial with order equals to what? Let's say with the order equals to 10, right? When the order is equals to 10, that's more flexible, right? So it's more complicated. So we have a low bias. You see that? The bias is low, but the variance is high. Okay. On the other hand, when the model complexity is low, that means like order equals to what? Order equals to 1. So for the linear model, it's very simple. So the bias is high, but the variance is low. So what is the best model? The best model should look at this test error curve. We should find somewhere that's at the bottom for the test curve. So that is somewhere between not too simple model and not too complicated. It's somewhere between. And that is how we select the best model. Okay? So, and through and that is the underlying mechanism is through the bias variance trade-off. Okay? So this is the MSE, mean squared error, based on, remember we also have a test set. Test set is that too. That's has the x value on a fine grid, but the true function value without noise. So that too only does not have this additive error, but just this fx. Okay, so you can see for the MSEs, right? And different curves, you can see we have different. So that means for the different data set, we have 50 training set. I simulated 50 training set. For each training set, I fitted 10 models. From one polynomial order is 1 to 10. So like this curve is one of the realization from one data set. I fitted 10 models, let's say. Okay, so just like that, so we have these 50 blue curves in the background. And what is the red one? Red one is the one that is the average over these 50 curves. So then what is the best model? The best model you can see here is this one, right? So on the average, when the polynomial order is 6, that's the best. And that agree with the truth, because the truth is for when the polynomial order is 6, that means we have 4 inflection point. What is the inflection point? Inflection point are the curvature change the signs. That means the second order derivative change the signs. Okay, so why this is the one? Because let me show you that. Because the true function is what? the true function is this one. Okay, between 1 and 10. So it has 4 inflection points, which is agree with the polynomial is 6. When the polynomial is 6, it also has 4 inflection points. So that means this is just show you that. So in this simulation, you should have a better understanding for the what is bias variance trade-off and how do we find out the optimal models. Okay, so this is the bias and the variance. So the orange curve, you can see that's the variance, and for the red dash line, that's the bias square, and the blue one, that's the MSE. Okay, so the MSE is the sum of the bias square and the variance, and also should plus the irreducible error, right? Why I didn't have the irreducible error here? Because in here, in this special example, I'm just having the test set is without error. So that's why the MSE is equals to the bias square plus the variance. That's it. Because we don't, for the test set, I didn't put the additive noise. Okay, so that's the two simulations. And these slides is talking about some math behind the bias variance trade-off. Okay, you may ask why the MSE is the summation of the variance and bias, right? So these questions can be easily answered through the rigorous mathematical proof. Okay, so this course is so to prove these is not the purpose for this course, but I put it here. If you want, if you are interested in that, because I know some of you are from the math department, so if some of you are interested, you can take a look, and the proof is not difficult. So the key is that all the cross product terms are all zero. Okay, like why this cross product term is zero? Because for this term, the expectation of the beta hat is equals to the beta. So that's why is equals to zero. Okay, so it's so to prove this is very straightforward. Okay, so this the third simulation is a classification example. Okay, so I want to still through this simulation, you will see the bias variance trade-off also applies to the classification case. Okay, so here I designed this simulation by that the x1, x2 are both IID from the uniform distribution, which between -1 and 1 for both x. Okay, and the response is following a Bernoulli distribution, but separated by the sign function. Okay, so in other words, for the so we have two class, the blue cross and the red circle. So the chance of having the blue cross above the sign function is 0.8. And the chance of having the red circle above the sign function is 0.2. Okay, similarly, the probability for getting the red circle below the sign function is 0.8. But the probability of getting the red or blue cross below the sign function is 0.2. Okay, so that's the underlying truth. And then I use the k nearest neighbors to do the classifications. Okay, so these are the sample code. You can play with that by yourself. So you can see I showed the underlying true boundary, which is a sign function, right? And I have three KNN results. Okay, so the first one is the blue one. So you can see the blue one is here. Blue one is the simplest one because also because the K is 21. So remember, the larger the K, that's the neighborhood size. The larger the K, the simpler the classification boundary is, the simpler the model is. When the K decreases, you can see the class boundary. Red one is more complicated than the blue one, so that is more complicated. When the boundary is dark green, that means the K is 3. So that's the most complicated one. Okay, so these are the code. So now we're examining the bias and the variance on 2 points. One is this one is this one. And the class boundary is here. So tell me, what is the difficult point to do the classification? And of course, it's this one, right? Why? Because this is close to the boundary. This is considered as an easy point to classify because this is away from the boundary. So most likely, this point will have a very good prediction results because it's far away from the boundaries. But this one, which is very close to the boundary, that is the one is difficult to classify. Okay, so the coordinates for this one is negative 0.5 for the x1 and 0.5 for the x2. But for this one is 0 for the x1 and then 0.1 for the x2. Okay, so that is 0 and 0.1, and this one is negative 0.5 and 0.5. That's the coordinate for these two. Okay, so let's see the bias variance trade-off. Still, I'm running 100 data sets, multiple data sets. Okay, so each time we do a classification, and we can also find the probabilities because we have multiple times, right? So you can see here, the blue one is the true value, and the red dashed line is the predicted value. Okay, so what is the true value? True value is 0.8. Why? Remember, this follows a binomial distribution, a Bernoulli distribution. So the probability for these 2 points to be the blue cross is what? 0.8. Remember? So it follows the BER means Bernoulli distribution with probability is equals to 0.8. So the probability of getting a blue cross above the sign function is 0.8. Okay, so that's why you can see the true value in terms of the probability for these 2 points are 0.8. Okay, and the top row is for the difficult point, which are 0 and 0.1. The bottom row is for the easy point. Is that clear? So the top row is for what? It is for this point. That's a difficult point. That's the top row. And this is the bottom row that shows. Okay, so so now let's see. For the top row, let's look at the top row first. And you can see when the K is 21, the model is what? Very simple because the K is large. When the neighborhood size is large, that means the fitted boundary will be smooth and simple, relatively simple model. So you can see the bias is 0.15 in terms of the probability. standard deviation is 0.08. But when we reduce the k, that means the model becomes more complicated. You can see the bias decreases, but the standard deviation increases. When we further reduce the k, the model is more complicated. When that becomes, the bias is 0, but the standard deviation is much larger, 0.25. So you can still see the bias variance trade-off. From this side, left side is the simple model, simple, but from this side is complicated model, right? So when we have a simple model, you can see the bias is large, but the variance is small. But for the complicated model, bias is small, but the variance is large. Okay, so that's for the top row. For the bottom row, it's slightly different because the bottom row, remember, is an easy data point. So even we have a very large k, that means the model is simple, the bias is still 0. Why? Because that's an easy point. Even for the simple model, we can have a good prediction, right? However, when we further make the model more and more complicated, the bias actually goes in the reverse direction. The bias increase because it's too variable. So it's most likely, so it's close to 0, but may not be exactly 0 because the variance is huge. Okay, so through this example, you can see the bias variance trade-off still exists for the classification, okay? And these shows the, so in the background, you can see we have 100 gray curves. Each curve represents a what? A data set. We have 100, right? So each curve represents a data set with, I fitted k and n's with different k size, okay? From k equals to 1 to 21. Okay, and the blue one is the average of the misclassification rate for these 100 curves. And you can see which one gives us the best misclassification rate, lowest. So you can see when the k is 9. So when the k equals to 9, this on the average gives the best results. Okay, so this is the supervised learning part. Now we talk about unsupervised learning. So what is unsupervised learning? As I said last time, unsupervised learning is like the supervised learning, but the difference is that it does not have a response variable. It only has X. So we don't have a gold standard to evaluate how good the model is. Okay, so that's why it's more challenging and more subjective for the unsupervised learning. Okay, but what are the typical questions for the unsupervised learning? Since we don't have a Y, we cannot do regression or classification, but we can ask, is there an informative way to visualize the data, to reduce the dimension of the data? And can we discover any subgroup structures among the variables or among the observations? Can we find some clustering patterns like that? These questions are the typical questions for unsupervised learning. Okay, so, and often unsupervised learning can be used as a part of the exploratory data analysis. Okay, so I listed 3 examples. The first one is to analyze the gene expression levels in the breast cancer patients. So we can try to find out the subgroups among the breast cancer samples. Okay, and this one, the second one, is to identify the group of online shopper with the similar browsing and the shopping histories. Okay, so if we can find out these groups, then we can send out these coupons and advertisement differently for different groups. And we can try to find those matching coupons and advertisements that can be very interesting to these group members. Okay, so that's also commonly used. And the third one is a search engine might choose what search result to display to a particular individual based on the click histories of others with similar search patterns. Okay, so that are three examples for the unsupervised learning. So this is the gene clustering example. So here we have three types of cancers, and we have the patient's gene expression levels, and these are expressed through the heat map. Heat map use the red and green to show the numerical values for each cell. So when it's red, that means it's above the average. When it's green, means it's below the average. When it's dark, that means it's close to the average. Okay, so you you can see here we have some groupings. Okay, and we will talk about this in details when we reach the clustering analysis. Okay, so you can see we can find some groupings, right? So these green groups tends to have what? High values for these genes, but relatively low values for these group of genes, right? But for the red group tends to have high values on this group of genes, but low values on these. So these are called genetic signatures. So these are the signatures for a, for for the breast cancer patients. Okay, so we can study these gene expression levels for these signature genes to see if their expression level is above the average or below the average. Let's say if you give me a new patient, okay, so if the patients for these genes, their expression level is below the average, then most likely they will fall to the green clusters. Okay, otherwise it may be falls to the red clusters and so on. So you can see to find out the underlying subgroups and the clustering structures are very useful in practice. And this is another example for the unsupervised learning. So this is a market basket analysis, and we will also talk about that at the end of this semester. And the MBA is to find out the market basket analysis. MBA is trying to find out the frequent patterns and the associations or the causal structures among the set of items in the transaction database. For example, like among all the transactions from a particular grocery store, let's say Walmart, maybe, if that transaction basket contains milk, okay, let's say, then 71% of chance that basket also contains bread, and 43% of chance it contains egg, 29 contains the toilet paper. Okay, so you can see there is a very strong connection or the associations between the milk and the bread, right? And these are the, of course, we know these associations, but this just as an example, okay? But then if we know that, what should we do? Then the retailers should what? Trying to put the milk and bread very to to the closed place so that the customer can easily grab the milk and the bread at the same location. That Did that make sense? But we can also do it in the opposite way. We can put these two very far from each other. But through the path that connects the bread and milk, we can put something that may attract these type of customers. For example, we can put some egg on the pass because 43% of them also buying egg. How about that? So then with that particular displaying these milk and bread and egg can maybe can promote those customers to buy more eggs, right? So these are very useful techniques, especially in the marketings and the selling for the grocery stores. Okay, so the last one is this is related to the image analysis. This example is called eigen face. We will talk about what is eigen, okay, for the when we reach the principal component analysis. For the PCA, principal component analysis, we will talk about what is eigenvector, eigen values, these things. So anyway, think about you have an image database, okay? You have millions or billions of pictures. And how do you summarize these pictures? And how do you represent these pictures not as each individual pictures, but as something more informative and also can reduce the size? So what we can do is among these, let's say millions of pictures, we can find some eigenface. Like here we have 4 eigenface, okay? And these you can think about as like a Photoshop. So each eigenface is like can stack to each other, okay, with different weights, okay. So like to have the best approximation of this picture, we can have like 0.1 weight for this eigenface, 0.3 for this eigenface, negative 0.1 for this, and 0 for this. If we have all these 4 eigenfaces with these particular weights, we can have an image which is very close to this. Okay, of course, this is just a very simple example. Usually, we can have thousands of eigenfaces. Okay, and we have these weights for each eigenface. Okay, so then we can have a very good approximation of these just by these weighting values, these weighting numbers. So instead of say store these millions of pictures, maybe we can just store a few eigenfaces. And then for all the pictures in the that you stored can be represented by a numeric vector, which is the weighting scheme for these eigenfaces. So that not just reduced the size, storage size, but also can be a good way to represent these high dimensional image data through the low dimensions. So then that makes it possible for human beings to visualize these high dimension data in low dimensions. And that technique in statistics called the PCA. Okay, and we will talk about that later. And this is also unsupervised learning. Okay, so the last slides just show you the different language between the computer science and statistics. We know that the machine learning is developed from the computer science area, and so they use different language, different words, but that may be that has a corresponding different words that we use in the statistics. Okay, so this table just listed a few. Like in machine learning, you will see network, graphs, and in statistics, that corresponds to models. In machine learning, we talk about the weights, And in statistics, we talk about the parameters. In machine learning, we talk about learnings. But in statistics, we talk about the fittings. They are essentially the same. In machine learning, we talk about the generalizations. But in statistics, we talk about test set performance. And supervised learning in statistics, we use the regressions, classification, depends on what task that we are doing. For the unsupervised learning in statistics, we talk about density estimation, clustering, and so on. Okay, so that's the different language that people use in these two fields. And a paper which is highly recommended if you have time to read it. That's I mentioned that the last time, the statistical modeling, the two cultures by Leo Berman, and this is a very good paper and not technical, easy to be understood. So just read that, and you will have lots of insights. And so the main point from this table, from this paper is the statisticians rely too heavily on data modelings. And these statisticians are the traditional statisticians. Nowadays it changes, okay? But machine learning techniques are making progress by instead relying on the predictive accuracy of the models. Okay? Okay, so this is so we finished the introduction to the statistical learning. And actually we have another topic is the model assessment and selection. So I will talk part of it and maybe finish that next time. So before we talk about assessment and selections, we need to talk about loss function, right? So what is the loss function? Depends on the task. If we have a quantitative response, that will be a regression problem, right? So we have two popular loss functions are the squared error loss and absolute error loss. But these are not the only two. We have some others like the Huber loss and percentage error loss and others. But the squared error loss is the most common one, and followed by the absolute error loss. So you may ask why we need to have more than one, because they have different properties. Okay, for the squared error loss, the good side is what? It's easy to find out the optimal solution if we use that. So it's efficient in the way that it's very computationally efficient to find out the solution that minimize the squared error loss. Okay, and also it is strongly supported by lots of theorems, theoretical results based on the squared error loss. Okay, so that's lots of theories. Okay, but the drawback is what? But the drawback for the square error loss is since it takes the square, it can be easily dominated by those outliers. Okay, think about the residuals. Okay, E equals to the Y minus F hat. Think about we have 100 observations, and most of their residuals are close to the 1 or negative 1, right? Let's say. But we have one observation which has the residual equals to 100. So based on the squared error loss, all these 99 data points is useless. Why? Because when you take the square, this one becomes what? This one becomes 10,000. Is that right? So all the others added together is just 99. This add together because 1 takes the square is 1. Negative 1 takes the square is negative, is also 1. So you add them together is 99. But this one is 10,000, which is much larger than this. So this observation dominates. So that's no good. Okay, so that's the drawback for the using the squared error loss if we have some extreme outliers. But absolute error is better, relieve that a little bit because it's not taking the square but using the absolute value. Okay, so for the typical choice, for the categorical response, we can have the 0-1 loss. If it's misclassified, the loss is 1. If it's correctly classified, it's 0. And deviance is another one. So which one is better? It depends. But this one is highly interpretable because we know what is 0-1 loss. It's easily interpreted because that is the percentage of error rate or the misclassification error rate, right? But the drawback is this one, 0-1 loss, is not continuous. It's discrete. So optimization for the 0-1 loss is very difficult. On the other hand, -2 log likelihood, which is the deviance, is continuous. And it's easy to be optimized. And for the computation, it's very efficient. But there's no direct way to interpret. Okay, so we will talk about more about these. Okay, later. So then let's see, we have training error, test error, in-sample error, and the generalization error. So these 4 definitions are very important. So training error, that's obvious. You have a training set, you fit the models, and you see the model performance on the training sample. That's the training error. What's a test error? That's also obvious. After you fit a model from the training set, and you make the predictions on the test samples, and the test error is the average loss over that independent test samples. So that's the test error. Okay, so the difficult ones are these in-sample error and the generalization error. So in-sample error is what? It's the expected prediction error condition on the training set. What does that mean? That means, let's say, suppose, just for the very simple case, okay, we have 3 observations, X and Y. Okay, so we have X equals to 1, 2, and 3. And let's say we have 3 Ys. Okay, so Y1, Y2, and Y3. Right? So this is our data set. Okay, so then after that, we can fit a model based on this data set. Okay, then that model's performance on this data set is called training error. Then if we have a new data set, that's test error. But what is in-sample error? In-sample error is that we conditioned on this 1, 2, 3, we didn't change, but we resample the Ys by fixing the X. And you may ask, how does that possible? Remember, our model is Yi equals to what? Fxi plus the epsilon I. Is that right? If X, let's say, is 1, the Yi will change. Why? Because the Yi will change because the Yi equals to what? Fxi. Xi didn't change. That means this part didn't change. But epsilon I changes. That's random error. So we can go back to the population and get another Y with the X is fixed at 1. Okay, so now we have a different set of Y 1, 2, 3. So I put a star, let's say I1 star, I2 or Y2 star, and the Y3 star. That's a new data set. Okay, new. Right? But X is fixed at 1, 2, 3. And then you can see we have some errors. Right? evaluate its MSEs. Not on the training set, but this time I use the training set to fit the model. After that, I evaluate the model performance using the new YIs. So I have the prediction error. Is that right? But that prediction error depends on these YI stars. So it's a random. If I change a new set of data points, it could be a different value. So the expected prediction error for this, that's called in-sample error. Why it's called in-sample? In-sample is because the X are exactly the same as the test sample X, but the Y changes. Okay, so the next one is called the generalization error. If you understand the in-sample error, then that will be very easy to understand because that has another name called extra sample error. That does not condition on the same X. That could be a different X. Let's say the first one is 0.9, then the second one is not 2, but 1.5, and the third one is 2.6. Now you can see we have a new set of X. And then I use the training model to predict on this new data set. Of course, we have the YIs also. So that's called extra sample error. And that is the expected prediction error over an independent test sample, not necessarily on the same X as the training set. Okay, so which error we are trying to optimize? Ideally, if you want to fit a model and you want the model to be an ideal model, so which error is really the main focus? Most of the time, I would say it's generalization error. Because we want the model to be generalized, can have a good prediction performance on an independent test set. Right? So that's the ultimate goal, to find out the model that minimize or optimize the generalization error. Okay, but it's not easy. Okay, this one ideal but not easy to be achieved. So what we can do is we first trying to see if we can find a model to minimize the in-sample error. Then we can go one step further to minimize for the generalization. Okay. So there were so why generalization performance is important, because if evaluation of this performance is important because we can use that to help us to select optimal models and also to evaluate how good the model is. Okay, and there are three types of model assessment. The first one is the in-sample error approach. The second one is the internal approach, and the third one is the external approach. We will talk about all three. Okay, for the in-sample approach, it's the performance on the sample used to develop the model. So we don't need to have a test sample. Okay, we just use the training set, but we do have a way to get the in-sample error minimized, and you will see in a minute. Okay, the internal is to split the data into multiple parts. We can have using the cross-validation or validation. These are the internal approach. External approach, that means if we have large enough sample size, we can leave a part of the data out to fit the model and then to assess the model using that independent test set. Okay, so that's the external. And for the in-sample error, that is the one that minimized in-sample errors that we talk. But for these two, we are trying to minimize or optimize the extra sample or the generalization error. Okay. So I've already mentioned this, so I'm just skip that. So for the in-sample optimism, okay. So for this picture, I mean, these when the model complexity is high, you can see the test performance and the training performance, there's a big gap. And that is a good indication for what? Overfitting. Do you remember? Overfitting, okay? For these, usually it's underfitting. Underfitting. And this is the optimal ones, okay? So these are the optimal ones. So for the in-sample optimism, let's just see that T is the notation for the training set. Y0 is the new end response value at each of the training points. And that's what I mentioned minutes ago. These are the new Ys, but with the X is fixed at training point. Okay, so what is the in-sample optimism? In-sample optimism, OP, is defined as this one. Okay, so what is this? This one is the training error. That's easy. Okay, you have a training set. Of course, you can find the training error. But what about this one? This one is the loss of the fitted model on the new YIs conditioned on the training set. In other words, we use this training set to fit the models and then do the prediction on the new Y zeros. And these are the new response of Y at each of the training points. Okay, and then we take the expected value. And then divide by 1 over n, because that's the average of the expected value for the predictions on the same x but different yi's. Okay, so that's the optimism. And this is still considered as a random variable. Why? Because here you can see this depends on the training set. In the training sets, we also have the yi's for the training set. And these are the random variable. If I change the training set, change the yi's, this will also change. The model will be changed. Of course, everything will change. So this is also a random variable. So this is the expected value for the optimism in terms of the yi's on the training set. So you can see these are the different expectation. This expectation is over the y0. That's the new yi's. But here the expectation is on the y's. That's on the training set. There are subtle difference, okay? That is equals to this for many models, not for all. For many models, we can rigorously prove that the expected value for this OP in terms of these yi's on the training set is equals to this. Then you may ask, for what type of models this follows? If we use for the squared error loss, remember squared error loss? We talk about that here. If for the squared error loss, this one, right? If the model used the squared error loss, then that works. But also if we use 0-1 loss, that's for the classification, or some of the other loss, we can show that this works. Okay, so now if you understand that, okay, oh, and by the way, you can see the expected value for the optimism in sample optimism is what? Is this one. What is the COV? That's the covariance. Okay, so that's the covariance between the yi hat and the yi. Okay, so what is covariance? Okay, so these are the basics. So that's why the prerequisite asks you to know the fundamental statistics. So you make sure you know what is, if you know variance, I think it's not difficult to understand covariance, right? So what is variance? Variance is, let's say, is y minus what? Expected value of y times y minus expected value of y. And that whole thing, take the expected value. And you may ask why I didn't put a square instead of write it out. Because, so this is the variance of y. But what about the covariance, let's say, of x and y? It's very similar to that. The only thing difference is what? Now we have x and y. What's the covariance? That's the expected value of x minus ex times y minus ey. So that's why I'm writing out in this way. So you can easily see, oh, that is the covariance of x and y. Is that clear? So similarly here, instead of the x, we are having the y hat. That's the only difference. It's notation. Okay, so what does that mean? That's important. So the covariance of yi hat and yi. So first of all, if we talk about the covariance, these two must all be random variable. So yi is a random variable. That makes sense because yi can change. Yi is random because we have an additive noise, right? But what about yi hat? That also can be changed because that depends on the training set, right? If training set different, yi hat will be different. Okay, so ideally, think about ideal case. Remember, the general model is y equals to fx plus epsilon, right? So ideally, what is the yi hat should be? The model should estimate what? Yi hat is not estimating y. The ideal case, the perfect case is the yi hat is estimating what? Is estimating fx. Remember? That's the ideal case. Okay? That's the goal. We want to have the yi hat should estimate f. Let's say in the ideal case, if yi hat equals to f xi, that's the ideal case. Then what is the covariance? The covariance is 0. And you may be shocked, but it's not. Why? Because fxi is a constant. It's not a random variable. Constant means that x is measured without any additive errors. X is an x. Fx, that's the deterministic part. There's no randomness here. You give me an x, the fx is fixed. It's not random, right? It's not f hat, okay? It's not the fitted model, it's the truth, okay? So this is fixed, and the yi is random. But if we have a covariance for a random variable with a fixed value, which is not a random variable, then it's always 0. So ideal case, this one will be 0. So that means the expected value for the optimism is 0. So that's the ideal case. Okay, but in the reality, most likely we cannot get 0, right? So that means what? So the COV, the covariance is taken over the randomness of y with x held fixed, and the expected value of the optimism. That is the amount of self-influence that yi has on the yi hat. So that is because the reason in the reality this is positive because that's just the overfitting. Okay, when the model overfits, so we are not fitting the f, we are fitting the yi. So this yi hat is highly influenced by the yi because yi contains the epsilon I. Remember? So in that way, they will have a positive covariance. And if the model is too adapted to the data, then this one, the yi hat will be the yi exactly. Then the covariance of yi hat and yi will becomes what? Will becomes the variance of yi. That will be large. Okay, so you can see in the worst case, the expected value will be this one, variance of yi. And in the ideal case, it will be 0. Okay, so but the smaller the better. Okay, for the overfitted model, this one will be large. Okay, after we get that, then let's go back to what is the in-sample error approach. We are trying to optimize the performance on the sample used. So in-sample approach is just trying to optimize the in-sample error. Okay, we want to estimate, or we want to optimize that, right? We can do it in 2 ways. Just using the training error, that's no good. Why? Because you can see there is a gap. That's called, the gap is the optimism. So just using the training error is no good. And that is showed here also. If we just choose the model based on training error, which model we should choose? Of course, we should choose this one, because that gives the best training error. But in reality, it's the worst. It could be the worst, right? Because it's overfitting. Because the expected value for this is huge. So which one we should use? Since we want to minimize that, so how about we are finding the model that minimize OP plus the training error? Can we? So in other words, we move the training error to the left-hand side. Is that clear? So that is our way to find out this. We want to find out the one that minimizes this by just using the training error, then plus the OP. But then you say, wait a minute, we don't know the OP. Yes, we don't know the OP, you are right. But here we can use, instead of using the OP, we can use this one. So that is the expected value of OP. And you may ask, how do we find out that? We can find out that by using this formula. And also, if the model is additive, just like this assumption, then we can show that the expected value is equal to this. So that can be also written as the training error plus what? Replace this by the 2 times the d over n times the sigma epsilon square. So that is the one can be used. If we find the model to minimize that, that is the one most likely will minimize the in-sample error. Okay, and that's the idea. So now you can see this is exactly the Mallow CP that we talked about. Mallow CP is to find out the model that minimizes the training error plus this one. What is this one? That is the expected value for the optimism. Okay, and AIC is what? AIC is more general. It's applicable to a more general applicable estimate of the in-sample error when a log likelihood loss function is used. So AIC is just this one. So AIC is equivalent to the CP if we have a Gaussian model. So what is Gaussian model? Gaussian model says that, Gaussian model says that the error follows a normal distribution. Okay, so that's the Gaussian model. If that's the Gaussian model, AIC and Mallow CP are the same. But this one is more general. it doesn't have to be normally distributed. It can be like a Poisson distribution, a binomial distribution, like that. So that's why AIC can be applied to more general case. So later we will talk about generalized linear model. So we cannot use MALO-CP. MALO-CP only for the squared error loss. So we can use AIC. Okay. Another one is a BIC. You've already see that. It's this one. So you can see AIC, BIC are almost the same. Why I say it's almost the same? Don't worry about this n at the denominator. That's just a constant. We can multiply it by m, which makes it very much the same, right? We always choose the smallest. So multiply by a constant, it does not matter, okay? So the only difference is that the coefficient, or we can say the penalty, is different. Okay? So for the AIC, the penalty here is this one. Okay, what is the penalty, right? That also related to the lasso ridge elastic net that we talked about last week. Okay, what is the first part? Or what is this part? These are all, if you're familiar with the statistical model, you know that these first term on the right side, these are the measure for how good the model fits the data. So the first part is the goodness of fit for the model. But these are all based on the training set. Not necessarily means that good. Okay, because you know that, so still just remember the training error low doesn't mean it is good. It could be overfitting, right? So we need to have what? Have a penalty. Penalty on what? Penalty on the model complexity. Because if we don't have that penalty, there will be problematic. That will cause us to have overfittings, right? So to have a penalty, then how to describe the model complexity? So that's part we describe the model complexity through what? D is the number of parameters in a model. So how many parameters do you have in a model? Like for a linear regression, for a simple linear regression, okay? Y equals to beta 0, that's the intercept, plus beta 1 x plus epsilon. So how many parameters do we have? We have two, beta 0 and beta 1, right? We have two parameters. So D equals to 2. Okay. So the number of parameters in the model is a good way to measure how complex the model is. And then multiplied by a penalty. So here for the AIC, we double the penalty. We double the number of parameters. But for BIC, it's log of the sample size. N is the sample size, training sample size. So this log N, most of time is much bigger than 2. Is that right? If you use calculator, you will see that log 10 is more than 2, right? So if the sample size is more than 10, that's already more than 2. So it has more penalty on the model complexity. So that's the difference. And we can talk about more details later if you are interested, okay? So anyway, this is the in-sample approach. And let's see examples. So this is the phone name examples. For the phone name examples, we have, it's a classification problem. We have two class, okay? And this is a speech recognition example. So the voice is recorded and represented through a technique called log periodograms. So these are the log periodograms measured at 256 frequencies. And the response, we have two class, two sounds. One is the R and one is the R. this like a water, vowel in the water, and this like a dark vowel in the dark. And we want to classify classify these two sounds. To the training set, we have 1,000 test that, and you can see we have these are the 15 parallelograms for each class. And here, the left panel shows the using the log likelihood, okay, and with the number of basis functions for the models. So here I'm using the logistic regression. We will talk about that with the spline basis function. We will also talk about that later. But just keep in mind is the more the number of basis function, the more complicated it is. That's the number of parameters. Okay, so the one that I highlighted on the horizontal axis shows the number of parameters. So the more complicated the model is. Okay, so you can see here we have three curves. The orange one is the training error. So you can see the training error. Oh, yeah, sorry. So the training error is monotonically decreasing, right? So, but the test error, which is in the blue curve, test error, that's the U-shaped curve. And you can see the AIC, that's the green curve. It's also U-shaped. So you can see the AIC and the test curve, they follows the same shape. So we can easily use the AIC to choose the best model like this. This is probably the optimal. That's the one that minimized AIC. And that's the one also minimized the test error. But remember, for the AIC, we only use the training set. We didn't touch the test set. Okay, but for the test set, that's totally based on an independent test set. So you can see by using the AIC, we can have a good approximation of what the behavior looks like when we evaluate on an independent test set. Okay, and this is the right panel is the misclassification error. Similarly, you can see the training error monotonically decreasing, but the test error and the AICs, they have U-shaped. So this example just show you that the AIC works very well in practice. Okay, so AIC or BIC, that's a question, right? So actually, we have more than two information criteria. Okay, we have about 10 or even more information criteria. So I know we have AIC, BIC, and we have DIC, and we have VIC, we have FIC, and there were lots of ICs. So, but these are the two most commonly used. And a lower AIC means a model is considered to be closest to the truth. But a lower BIC means a model is considered to be more likely to be the true model. So they are different, very subtle difference. What is the subtle difference? Because the AIC doesn't assume the model space that we explored, including the truth. It only, so think about like here, the model space that we explored are here. Let's say we are considering all the linear model. Suppose the truth, so the true model is nonlinear, is outside the linear model space. Let's say this is the truth. So what does AIC tell you? Technically, AIC, if you have large enough sample size, we can prove that if you have large enough sample size, the sample size increase. So the AIC will give you the model which is closest, like this one. That will be the AIC selected model if we have large enough sample, because this is closest to the true model. Okay, but what is BIC? BIC is more likely to be, so in the BIC settings, if the model space is here, the true model is inside the model space. And using the BIC, and if we have large enough sample space, if we have large enough sample size, and what is the true, or what is the BIC model will be selected. The one that we selected is exactly the one that is the true model located. So that's the BIC settings. So you can see there are subtle difference. Okay, and also AIC put less penalty on the model complexity, and the BIC put more penalty on the model complexity. So in general, the AIC tends to select more complicated models than the BIC because BIC put more penalty on the model complexity. So the BIC usually selects the simpler model compared to the AIC's model. Okay, so let's stop here, and next time I will continue and finish the assessments for the validation approach and leave one out cross-validation. Just read the slides and we will move on faster. Okay, let's stop here.